How did complex life evolve on this planet? It's a really fundamental question that we don't really understand. What types of environments did it evolve in? Could there be complex life elsewhere in the universe? These are the kinds of questions that we might be able to have a better idea about if we can understand how it happened on our own planet. I work on really early life, how life became complex, how we went from a world with just microorganisms like bacteria and archaea to one with complex organisms, multicellular organisms and animals. Earth is 4.5 billion years old. If you went to any museum around the world, all the fossils that you'd pretty much see, the dinosaurs, the trilobites, the ammonites, they all come from the last 10% of that history, the last 550 million years or so. Here we have rocks that are older than that. These date to about 900 million years. We're 6,000 feet up in the mountains here, and these rocks were deposited in an ocean. It doesn't look like an ocean today, and that's because of plate tectonics. We can actually go to these outcrops on land and we can find the fossils that we want to document life's history.
In order to get into the field area, which is located in the Mackenzie Mountains, right along the Yukon Northwest Territories border, we have a pretty complex logistical plan. Once the helicopter drops our entire crew off, we're really isolated from any form of civilization.
Science and a project like this is a real team effort. I need people like geologists who are going to go out and tell me what environments my fossils are in so I can understand where these organisms were living.
Everybody brought along different types of researchers, including undergraduate students, graduate students, and postdoctoral scholars. Not only is the camp quite remote, but it's a very steep mountainous terrain. Every day we're climbing between 1,000 and 3,000 feet to the tops of these mountains, and there are no trails. For the most part, we're essentially bushwhacking through very thick brush and/or climbing up and down very steep loose talus. We are really fortunate to be on the traditional lands of the Seytu Dene people. They are aware of our work and supportive of us doing work in this area.
Over the last few years, I've been working on the types of rocks which preserve these early life forms. And those rocks tend to be fine-grained mudstones. It turns out that the muds have to have a very specific composition. They have antibacterial properties. Clays are really good at being toxic to the kinds of bacteria that will degrade our fossils over time. And these rocks have the right types of clay. So we should find really nice fossils here. My student George is here. His project is really to document the fossils that we find.
Some of the fossils that we're collecting out in the field are visible to the naked eye, but my work specifically focuses on microfossils. To recover those microfossils, we need to take our samples back to the lab in Oxford. There, we'll dissolve out the rock, leaving behind organic matter in suspension. I then take the organic matter, put it into Petri dishes and sort through it bit by bit.
We can hand-pick individual fossils out with a pipette, put them on a slide, and we'll be able to see them under a microscope and really document their morphology.
This fieldwork's been pretty tough, but it's really opened my eyes to this amazing environment to learn in.
It's really fun to spend a couple of weeks out here in the summer in the mountains, exploring ancient environments. I still get a thrill when you pick up that piece of rock and there's a fossil there. That thing has not seen anything for 900 million years. And that's really exciting. I'm very thankful that I get that opportunity to see these ancient organisms for the first time.